motivating theoretical talk. I will talk about praxis now. We try to commercialize. So we print, but we print powders. This makes us very different from all the other talks. When I give a talk, I have to start with something general, okay? And of course, when we talk about photovoltaics, we talk about energy, and when we talk about energy, this is connected with climate change, and climate change is really, really, really a bad threat, okay? I have to remind people. The Bulletin of the Atomic Scientist is a journal which warns against destruction of mankind, okay? They started this during the Cold War, when nuclear war was threatening us. But for them, meanwhile, climate change is the main threat. And they keep moving their warning clock, which has been already about 20 minutes before 12, after end of the Cold War. They keep moving this forward, and last year they reached 2 minutes before midnight because people do not act in case of climate change. The last results from the IPCC, the International Panel dealing with climate change, tell us that we have to reduce our CO2 emissions until 2030 by half at least. And Europe actually decided to become carbon neutral until this time. This means no more burning fossil fuels. This is really, really something, okay? Now, there is some hope because photovoltaic became the cheapest energy technologies. I guess several of you are not aware of this, but if you really look at the market prices and the lowest costs, you can see with 4.4 cents per kilowatt hour, this is my change scale there, 44 means 4.4 cents per kilowatt hour. PV is cheaper than everything else, cheaper than coal, cheaper than nuclear. Nuclear is much too expensive, twice as expensive. So I cannot understand why people still think about nuclear power. And the reason is a huge growth. PV is here yellow, and you see the yellow bars are smaller than the blue bars, which is wind energy, but it's rising faster. So PV will become more important than wind already within the next 2 years. Solar thermal systems, actually, which you have a lot here in Morocco, they are on a 5 gigawatt scale. The other scale is 500 gigawatt. Okay, so it's totally different scales, actually. So even in Germany, PV is cheaper than everything else, and half of the price is the price of the module already. So all the balance of systems costs become more and more important here, and further decrease of price will have to do a lot what happens in the sector of balance of systems costs. This is inverter costs, installation, and so on. But just looking at the modules, this was the development within the time I'm doing research. So this is the last 40 years. And the price dropped by a factor of 100, which means 2 times a factor of 10 within 20 years. And if we prolong this thing, just continuing what has happened in the past, you see we reach a size of production in the 140 terawatt range. And if 140 terawatt of photovoltaics should be installed one day, and the prediction here is 20 years. This is the energy demand of the world. This is 30 terawatt power provided by PV. All the energy of the world, okay? Here's a calculation what this, where this comes out, and this 30 terawatt actually with 144 terawatt peak installed, this 30 terawatt corresponds to producing, or the need to produce 3 square kilometers of photovoltaic modules per hour. This is a very fast production speed, and the question is, how can you do it? And this is why we started to work with a company which is printing, actually. So the company Forster in Austria makes these street signs, and this is their machine park. Commercial machines installed in this company used there. And we used these machines 1 day per week, converted them, and printed our modules. Okay? This is the company, founded in Tallinn, Estonia, actually, now mainly in Vienna. In Tallinn, we produce these little single crystal powders, and I have some sample here. So I will pass it around. You can have a look. It's glittering because the single crystal planes reflect the light. It looks quite nice. This is a powder which we ship then to Austria and produce modules. And in the introduction by Suzanne, thank you very much for inviting me, actually. But she did not tell you why we work on Kesterite, so I tell you why we work on Kesterite. Actually, it's earth-abundant components. Copper, zinc, tin are nearly, you can find in very many places on the world in abundance. It's not expensive. And coming from the peace movement, in which I worked for quite some time, it's quite nice that this is actually the ultimate conversion, because the combination of metals, copper, zinc, and tin, was called gunmetal, because this is where the guns were made from. This is a gun in Marrakesh, actually, made from this material, and we convert this gunmetal to solar cells, just by making the sulfides and selenites. So what we do is we grow these crystals by just putting the elements together. We put copper powder, zinc powder, tin powder, sulfur or selenium, or both of them, into an ampulla. We add some salt, which acts as a solvent, actually, because the salt melts, acts as a solvent, and you can see in this differential thermal analysis, you heat this up, nothing happens, and then the red peak, the salt melts, and when the salt melts, you form directly CZTS. You keep this ampulla at high temperature until the growth gives you the right size of your particles, and then you cool it down. It looks black, because the CZTS has formed. You just put this into water, the salt dissolves, and you have your powder. Very simple. And then you use the powder for printing. Yeah, you can print it endless, of course, the way we do this, actually. No, I don't want to pass it around, actually, because then everybody starts scratching on it, and then I have to use another one, maybe. This is not stably sealed yet. This is just with conventional polymer to protect it a little bit. You can touch it afterwards if you want. Okay. So this is how we do it. We print a plastic film or a polymer film on any substrate, because the substrate is afterwards removed. We put wires into it to make the series connection. We put the powder in. We make the front contact, also by printing, transparent, as you can see here. Then we seal the front side. We remove everything from the substrate so that we have access to the back side. We polish the back side mechanically. We open the grains, basically, and we print the back contact on the back side and seal the back side. That's how we make these modules, and this is how they look like. All these powder particles, which you see in this little box, are sitting side by side. They touch each other, but there is no conductivity within the film, so every particle actually is a separate solar cell. Okay, it already has a PN junction because we protect the surface of the CZTS, which we grow, with a buffer layer, which can contain cadmium or cannot contain cadmium. Still, the cadmium-containing buffer layers are about 10% better than the ones without cadmium, but both work, actually. And you have these transparent modules, which currently have an efficiency up to 9.5% in a cell. Typical efficiency of these is between 6 and 8% for the module, finally. Now, what is interesting is actually that this material is very, very homogeneous, okay? So this shows a current measurement, a current image, actually, of a small part of this cell. And you see from the color the current flowing. And when you plot this, you show that the current distribution is actually quite narrow. So we know that the quality of the powder crystals is within plus minus 3%. So it's very homogeneous. But to achieve this homogeneity, you have to do a few tricks, which I cannot tell you. So this shows this current distribution for different cells. And you can see the record cells finally have the most narrow distribution of this current behavior. Just a remark to the composition. We work with thermodynamically stable compositions, of course, and they are not always what we put into the ampulla. Of course, as Susan has shown you, you can vary the composition on a wide range, but then if the composition is not the final composition, in the formation of CZTS, you also form secondary phases, which means other compounds, zinc sulfide and tin sulfur selenide and whatever, lots of secondary phases, except if you start really with the right ratio of these metals. So if you start outside this oval, which is just enlarged on the right side, and it shows the copper content and the zinc content, just taking the content of tin as one, okay? If you start from outside, you will move into this oval, and if you start within the oval, you remain within the oval, so that you come up with one point, actually, where it's completely stable, where input ratio and output ratio is equal. Just another tip, of course, you can poison your material. So most of you probably work with the most pure materials. We want to produce and we want to use the most cheap materials, okay? These modules are made from 2N materials. When we want to make records, of course, we start with 6N materials, which are orders of magnitude more expensive. And the reason is that 2N material may contain certain poisons. And you see here an analysis. We just intentionally poisoned very pure material with certain metals, and you can see here which are critical and which are less critical. You can ask me for more information if you want to know more. So, we are already on the road since 2008, 10 years old already. We have these two facilities. These are funding agency and prizes we won. Of course, we can discuss about comparing different materials, and of course, one of the most promising new materials are the perovskites. In my opinion, perovskites, but we have more experienced people here, are not really stable in the presence of oxygen. So most tests are done in glove boxes or so. But if you expose them to oxygen, it becomes a problem with the stability. Our material is stable without sealing. Okay, so we have it 3,000 hours at 85 degrees. As long as there is no water, it's stable. So oxygen is not a problem here, but oxygen may well be a killer for organic solar cells. This is why actually I stopped with organic solar cells about 10 years ago, after having been the first one who really working with organic solar cells since 1988. At least if you don't count sensitization solar cell as organic. This has been done a little bit longer. Okay, so main application for us in the moment is building integration, because we can sell this stuff without sealing. This makes it much cheaper than all competitive materials. We think it's really a unique technology because we use single crystal. We have the best possible quality of the material. On the other hand, we print these single crystals, so it's very cheap production technology, very simple machine if you look at it, and you can visit us and have a look yourself. It will allow much lower prices. And we have to think about the future, of course, if we start a company, not about today. And PV will become cheaper, that's for sure. It's flexible, it's variable, it's stable, so it's unique. Thank you very much for your attention.